So for those of you who are attending this webinar for the first time, this is actually one of the topics that we cover in Advanced Java SE Programming with Passion course. So if you log in and these are the topics that we cover in this course. So we cover annotation and we cover generics, and today we are going to cover Java SE 5 concurrency. So we have about 15 topics including OSGI. So let's go to the presentation. By the way, just to clarify, we are not going to cover Java SE 7 join and fork scheme. We are going to cover that as part of the Java SE 7 topic again in this course. So concurrency utilities, they are defined as part of the standardization effort of JSR 166. It basically enables development of simple yet powerful multi-threaded application, and multi-threading application is becoming more important. So it is in fact sort of a framework, like a collection framework. So if you think about the collection framework provides rich data structure handling capability. So in the same way, concurrency framework handles this multi-threaded application development. So in fact, it could actually provide even better performance than C, especially for high-end server application. The reason we need this concurrency utilities framework is because the existing, before Java SE 5, existing schemes of writing multi-threading applications using wait, notify, and synchronize, they are just too primitive. So this concurrency framework and utilities enhance scalability and performance and readability and thread safety of your Java applications. So this is sort of the same kind of line of explanation why we need concurrency utilities. Basically, reduce the programming effort. Many people have written their own multi-threading applications, and now we can use concurrency utilities from Java SE 5 and above. And it increased performance because it's written better than typically homegrown utility multi-threading applications. Increased reliability. So basically idea is to eliminate threading headers such as the deadlock, starvation, race conditions, and excessive context switching. Those things are going to be actually taken care of. Also improve the maintainability and increase productivity. So it's kind of obvious reasons why we need a standardized concurrency framework and utilities. Okay, so we are going to cover more detail, concrete, the classes and interfaces of concurrency utilities of the Java SE 5. So these are the topics that we are going to cover. All right, so let's move on. So the most important feature of concurrency utilities framework is task scheduling framework. So what do I mean by that? Task scheduling framework is made of a set of interfaces and classes that actually standardized task submission and also implementation of a particular scheduling and executions are captured in the implementation. So we are going to actually spend quite a bit of time understanding these classes. So executor, executor service, and executors. So standardizing of task submissions and scheduling and executions are captured in the implementation. So executor is interface, and executor service is a subclass of executor, and executors is a factory class for creating various kinds of executor service implementations. So this executor service implementation capture a particular scheduling policy and execution policy. Okay, so this is just to give you a big picture of this set of interfaces and classes, and we are going to spend rest of this presentation looking over these interfaces and classes. So let's start with the executor interface. So executor interface provides a way of decoupling task submission from execution. Okay, so submission is standardized. In fact, the execute interface has what is called the execute method, and this is a method that you can use to submit your task. Okay, for example, you create runnable task and then you are going to use execute method of executor interface to submit. So this is the way that you are going to submit the task. Okay, so submission is standardized. Now, when you get a particular implementation of executor object, that the particular implementation is providing a particular implementation specific mechanics of how things are supposed to be run, including thread use, including scheduling, and things like that. Okay. All right, so there are several implementation classes of executor. Moving forward. In general, you are going to use executor service interface rather than executor interface. So executor service interface is extension of executor. So you can certainly use execute method on the executor service object, but it does provide a better way of submitting a task, which we are going to look into in the following slide. So executor service as two group of important methods. One is lifecycle management method. So you can shut down, shut down now, and you can check whether it is shut down, whether it's terminated, and await termination. So these are lifecycle management methods, okay, of your executor object. Another set of important methods that are added to executor service interface is new set of submit method. Okay, so instead of using execute method, now you can use a submit method of executor service interface. So here you can see it returns a future object. Okay, so let's see the difference between the two. So executor has execute method, and executor service interface added submit method. So when you have executor service object, you could use either execute method or submit method for submitting a task. Okay. However, in general, you are going to use a submit method because submit method provides more functionality. So submit, when you are using submit, it will return. So if you actually take a look at this definition of submit method, here it returns a future object. So we are going to take a look at the future object in a few minutes. Basically, by having a future object, you can find out information about the task that was studied. For example, once you got the, so in this case, so this is an example that you are going to start or actually submit a task by using execute method of execute interface. This is an example. So suppose you get the executor service object, and then you can use either execute or submit method. But when you're using submit method to submit your task, it will return the future object. And by using future object, you can actually perform a few things. For example, you can check whether the task has been done or not. Okay, so executor service interface provides more richer the method of submitting a task. So question from Diptash. What is executor and why to use it? So executor is interface. And executor, so let's move on because we're going to actually cover all those topics, how we can create an object instance of all these things in the rest of the presentation. Okay. So there is a factory class called the executors. Okay, so this is provided by the JDK, and you can create different executor service object. Okay, by calling different method. So by calling each of these different method, it will provide different implementation of executor service object. And each of these implementation implements different policy in terms of the thread size, in terms of scheduling and things like that. Okay, so we are going to actually look into each of these executor service object implementation in the rest of the presentation. Okay, so I want you to actually understand, we actually look into so far executor interface and then executor service interface, and then we are looking into factory class. This is the utility factory class called the executors, and you are going to select a different implementation of executor service object by calling different method depending on your need. Okay, so let's go over each of these methods in a bit more detail. Okay, so again, this is executor factory class we just looked at in the previous slide. And this method, when you're calling new fixed thread pool method and you provide the pool size, so basically the executor service object that is returned basically creates a thread pool that reuses a fixed number of threads, okay, operating on a shared unbounded queue. So it's actually using a queue internally, but that's not something that you have to remember for now. So this is how you are going to use this method. So you are going to use executors factory class, and then we are using this static method we just looked into over here, and then you provide the number of threads. So this is a pool size, meaning the number of thread pools. And then what it returns is executor service object, and then you are going to use a submit method to submit your task, and later on, and then it will return future object. And sorry, it looks like we have more than 100 people joining. So now you can actually use some of the method of the future object to find out the status of the submitted task. Okay, so let's do our first demo. So we are going to try the executed submit of this fixed. So we are going to try the execute first. So let's take a look at the code. It's very simple code. So in the main, we created fixed thread pool by calling new fixed thread pool, and the number of thread is 3. Okay, and then we are basically in a loop submitting my task object. So here we are creating 10 runnable tasks, and then submit to, well, actually in this case we are calling execute. So when you're calling execute, it doesn't return anything. So basically there is nothing that you can control. There is no way of actually controlling your task. Okay, so let's run this application. So it's a very simple application. It's basically just display, from the my task. So connect to remote host, connection refused to connect. Oh, actually I was running on the wrong code. Okay, so let me just go. Standalone example. Okay, so it's basically task 0 and 1, 2, 3, and 5, 6 is running. So if you take a look at the my task.java file, it's just displaying things inside this run method. Now let's take a look at the submit. I mean, it's actually doing the same thing, except that here we can receive a future object, and then we can check whether the status, we can check whether task is done or not by calling is done method. So if you take a look at the future Java doc, if you can do context sensitive Java doc, you can actually perform the information about is it canceled or is it done, and you can even cancel the task. Okay, so submit is actually more feature rich. Okay, so moving forward. Okay, so typically the way that you are going to use a multi-threading application is when you are receiving a request from the client, and you want to actually handle those number of clients in a pool of thread. Okay, so in pre-SE5 code, whenever you are getting suppose you are actually writing a web server, and you are receiving a request from the client, and whenever you receive a client, you are basically creating a new thread. Okay, and then run it. Okay, so here you are basically creating many number of threads. So instead you want to use a thread pool. So that's where we can actually use this new fixed thread pool. So we are assigning 7 threads to the pool, and then we are executing client request from the pool. So suppose there are 7 requests up and running, and then when there is another request coming in, that request will be blocked. Okay. All right. So let's do this exercise, this demo. So let's see the code. We have server code. So in this server code, we have main. So we are creating server port is 8100, and the pool size, we are going to just use a 2 as a pool size, so that we can actually see the symptoms when the third request comes in. Okay, so we created, so if you take a look at the server using executors Java code, we are basically creating the fixed thread pool with a pool size of 2. Okay, and so whenever and then it will call the service request. So inside the service request, we are performing a task. So connection handler task. This task is accepting the request coming from the client. Okay, so if you take a look at this code, it's just a runnable task that handles the request coming in from the client. So it will just display the message that connection is established, and then when the client sends the data, it will just display the data. Okay, and let's take a look at the client code, and then we will actually run this code. The client code is, it has nothing to do with the concurrency. It just kind of send the socket request to the server 8100, and then it will send the message to the server. Okay, so let's run the server. Run. So the server is now up and running. It's listening for connections. Okay, so remember, the server has only 2 threads in the pool. Okay, so we are going to now execute multiple instances of the client. So we are going to run the client. So run client. So here we are going to type in hello 1 and then enter, and then it will send this string to the server. Okay, so if you go back to the server, you can see the server now accepted the client connection, and then it displays the data that has sent from the client. Now let's run the second instance of the client. Okay, so second instance of client, we are going to send hello 2 and enter. Now again, if you go to the server, now connection second connection established. So this is handled by the thread 1, and this is handled by thread 2. So all threads in the thread pools are used up. So next time a client is trying to connect, so you're going to actually start the third instance of the client, and let's try to type hello 3. Okay, and then enter. Okay, now you can see if you go back to the server does not handle it because there is no thread in the thread pool to handle the third request. So what we are going to do is we are going to we are going to exit the second instance. So the way that you are going to exit the second instance is type exit and then press return. Now if you go back to the server is now should have the connection from the server. You can see connection 2 is ended, and then connection 3 started, and you can see the data coming from the client. Okay, so this is actually a very simple example in which you are writing a server taking advantage of this concurrency utilities of the fixed number of pool size. Okay. Yeah, I know there are some questions, so let me actually move on to the end, and then if we have time, then I'll actually address the questions, because I have to finish before 5 minutes before 12, because we have another webinar starting from 12. Okay. All right, so moving forward. Now let's talk about the new cached thread pool. So the way you're going to create the cached thread pool is again calling new cached thread pool. So the cached thread pool is going to create a new thread as needed basis. So as compared to, as opposed to fixed thread pool, you specify the fixed number of threads in the pool. But cached thread pool, you are basically making it flexible so that the number of threads in the pool can be increased depending on the need. Okay. In terms of usage of that method is the same. So again, you're going to use executor's factory class, and then you call new cached thread pool, and then you get executor service object, and then basically you submit your task. Okay, so same programming model. So that's the reason we say, you can see different executor service object capture different scheduling policy in terms of the pool size, in terms of, well, we actually see another example of the scheduling in the following slide. So, but as far as the programming model is concerned, it's the same. You basically use a submit method of executor service interface, and then you submit your task object. Okay, so this is a cached thread pool. So, nothing really peculiar about this. So here, instead of fixed pool, we are basically using cached pool, that's all. So this is the code, cached pool. And again, we are actually using the same code. We are, sending my task. So it should actually be exactly the same as the fixed size pool, okay? But if you actually increase, well, so the thing's actually working behind in a way that it will actually increase the number of the pool size, the threads in the pool size. Okay, moving forward. Now, this is another the executor another method. So here you can call new scheduled thread pool. Okay. So basically, it will create a thread pool that can schedule commands to run after given delay or to schedule periodically. So what it returns is scheduled executor service object. Okay, so this is a bit different, right? So in previous case, it will basically returns executor service object, right? Now, when you are calling new scheduled thread pool method, it will return scheduled executor service object. So it actually provides a bit more richer functionality in terms of scheduling. Okay, so this is how you are going to use that method. Again, you are going to call this method from the executor's factory class, provide the pool size, and then you get the scheduled executor service object. Now, this is how you can schedule the task. Okay, so instead of just submit, you can specify a bit more scheduling a bit more scheduling aspect of submitting. So here you can call schedule at fixed rate, and then you provide your task. Okay, and then you can provide initial delay, and then you can provide a period between successive execution. So you're actually repeating these things, and this is a time unit. Okay. So this is a bit more sophisticated than just a simple submit, right? So this is actually submitting your task in a scheduled fashion, okay? All right, so let's take a look at the scheduled pool standalone example. Here, so let's take a look at the code. So we call new scheduled thread pool, and the pool size is 3. And here we are studying two different tasks. One is called the timer printer task. It's just displaying the time, on standard output object. And this is initial delay. So we are studying this one after 1 second, and every 3 seconds, we want this timer task to display something, the time. And we are studying the second, the scheduled task. Okay, so here we are calling the we are submitting timer printer task number 2, and this is initial delay of 3 seconds, and then this is the duration between successive executions. Okay, and then it returns scheduled future object. Okay, now by using scheduled future object, if you can take a look at the code. So you can get the delay, you can cancel and things like that. Okay, and now here from the scheduled executor service object, we are scheduling another one, and in this case, we are basically scheduling the task. So this is the inner class object. Okay, so this is inner class object, and this inner class object will get run after 40 seconds, and when it runs, it's going to call time handler 1, which is this scheduled future object, and it will cancel. Okay, so as we have seen the Java documentation, we were able to call the cancel method, right? So, we can just call the cancel to cancel the task. Okay, so we are just canceling this too. Okay, so, and this timer printer task is nothing really, unusual. It's just printing things out. Okay, the new date, current time. Okay, so same thing is, it will just say timer print task 1, and this will just say timer print task 2. So if you run this guy, and it will just keep printing the current time from task 1 and task 2. Okay, so after 10 times, it will just be canceled, as we have seen in the code. Okay, so moving forward. Callables and features. So before Java SE5, we didn't have a scheme of finding out the result of callee thread. So this is what we are talking about. If a new thread, this is the callee thread or callable thread, is started in an application, there is no way to return a result from that thread, meaning callee thread, to the calling thread. Without the use of shared variable or appropriate synchronization. So you might in fact have session object in the web application that actually, basically whatever shared variable that can be shared between two threads, and that's actually one way of actually defining what's going on, but it's really clumsy, it's really complex. So callable and features are provided. We already have seen the example of feature. Okay, so callable and features are provided in Java SE5 concurrency framework. So callable thread or callee thread implements callable interface, and the callable interface has a call method. Okay, so you have to implement call method of callable interface. And calling thread submits a callable object to executor object and then moves on. So callable, the caller will actually do whatever it wants to do. And again, it will use a submit method, not execute method, because the execute method does not return feature, right? Submit method returned feature object. Later on, when the caller wants to know what happens, meaning result of the callee thread, it will call the get method of future object. So if the result is ready, it will be returned. If not, calling thread will block. So this is the callee. So this is a callee or callable thread. So your callable or callee thread, the class, has to implement callable interface. Okay. And what that means is that you are going to implement call method, and the result will be returned. So this is the type, generic type that is returned from this call method. This is caller, the method, and the caller, the code. So here we created executor service object, and then we are submitting your callable example object, which we have seen in the previous slide. So this is callee, and it will return future object of type of string, because that's what we defined in previous slide. And then later on, the caller will call get method of this future object to find out the result. All right, so let's do this demo. Callable and feature. So code is pretty simple. So let's take a look at the main code. So in the main code, we created execute a service object, and then we are submitting callable example, the task. Okay. So this should implement callable interface, and then we submit. Okay, and then we are slipping just 1,000 milliseconds just to simulate the business logic in this caller the thread, and then the first thread is a parent thread, is complete asking feature for result. Then it will call the get method of the feature object that we got when we submit this callable example task. Okay, and then we'll just display the result from result. Okay, so let's take a look at the callable example code. So callable example is again implements callable, the interface of type string, and it implements it. And here it will return me called thread successfully finished. So this is the result that is being returned from the callable callee thread to the caller thread. Okay, so let's run this application. Okay, so you can see me called thread is successfully finished is returned from the callable or callee thread to the caller thread. Okay, moving forward. Semaphores. I'm sure you have heard of semaphores. Semaphores are used to restrict access to fixed size pool of resources. So you are going to create a semaphore object using the same number of resources. Okay, and then you're going to the way that these semaphores are being used to control the access to the resources through acquire and release method. Okay, so when a client wants to use a resource, it has to acquire the semaphore first. And if the number of semaphore count is greater than 0, that means there are resources available, then it will return immediately. And if all resources are being used, that means semaphore count is again 0. In that case, any client trying to get an access will be blocked until some another thread releases the semaphore. Okay, so, and of course acquire and release are thread safe. So this is a semaphore example. So here the pool size, this is the pool size is the number of the resources. Okay, so we are going to create a semaphore specifying the size of resources. Okay, and then a method like a get resource method will be invoked by the client. Whenever they want to use a resource, they have to acquire semaphore first. Okay, so they are going to call acquire method of the semaphore object until semaphore is available. This user, the user that is calling this get resource method will be blocked. Okay, until another thread, another client returned the resource, return the resource and then call release method. In that case, semaphore count is incremented, and then whichever blocked client will be the return from this acquire method, and the user can use the resource. Okay, so let's try to see semaphore example 1 code. Okay, so let's take a look at the main code. So here we created basically we are creating a resource pool managed by semaphore, number of resources, and then we created execute a service object so that we can actually, this is actually trying to simulate multiple clients trying to use the resources. And then we are creating task, resource user task 1, resource user task 2, and resource user task 3. Okay, so it's going to, this is our own code, and it's passing resource pool that we are using, and thread ID is just passing a thread ID. This is a thread ID 2 and thread ID 3, and this is the run count and hold duration and pause duration. So basically, we are studying these 3 resource user tasks using this executor service, and later on we're going to just shut down. Okay. Now, when we are looking at this resource user task, let's take a look at this code. So here, basically, we are setting things up, and then it's going to run. So in this case, it's going to try to use a resource. So it's going to use, it's going to actually call the get resource method. Okay. So if you go to get resource method, it's going to acquire semaphore first to make sure, it has a resource to deal, to manipulate. Okay. And so once it is returned, that means resource is available, so it will just do whatever it has to do with the resource. Okay. And this is the put resource, meaning once it is done, it will return the resource. So, this put resource method will be invoked. So here we are basically do whatever business logic we have to do. In this case, we are just setting the false to this used array, and then we are going to call semaphore release. Okay. So this is what we just have seen. Okay, so we see both code. Okay, so if you run the code, so you can see, it's actually acquiring a resource and do something, and then release the resource, and it will just do those things like 5 or 6 times. Okay. Okay, so moving forward, concurrent collections. So it provides blocking queue interface is providing thread-safe way of multiple thread to manipulate the collection. And there are several implementations, and the array blocking queue is the simplest concrete implementations, and it provides a multiple set of methods: put, offer, pick, and take, and pause. So put is actually putting things into the queue. Offer is non-blocking, so it will just, place it and then it will move on. And pick is to see whether there is anything. Take is actually taking things out. Okay, so pick is just taking a look. It doesn't take things out. And the poll is just kind of to see actually, I don't know what poll is all about. Let's actually take a look at the Java documentation. Non-blocking and fixed time blocking. Oh, it's actually doing polling. Okay, all right. So this is a code blocking queue, the example here. So basically, from the queue, suppose we created this blocking queue object, and then we can either take it, and so you're actually taking an item from the queue, and here you are placing an item to the queue. Okay, so pretty straightforward. Okay, so blocking queue example. So one is a task that is placing message into the blocking queue, and the other one is a task that take item from the queue. Okay, so if you take a look at the main code, okay, so we created array blocking queue object. Okay, so let's take a look at the Java documentation. Yeah, it has a lot of methods. I'm trying to see. Oh, I'm looking at the wrong one. Sorry. I was actually looking at this guy. All right, so here offer, put, offer, pull. Okay, so this is the one I was looking for. Retrieves and removes the header of this queue and return null if the queue is empty. Okay, so all right, so we create the array blocking queue, and then we create the executor service, and then we are studying this task that is putting things into the blocking queue, and then we are studying another task that is taking things out from the blocking queue. Okay, and they use the same blocking queue, as you can see, and it basically uses a different starting time and the duration. Okay, so if you run the code. Oh, again, I'm actually looking at, yeah, this is not the main task, that's why. Okay, so blocking queue example run. Okay, so basically it's, the content of the message is sent to the queue, sender is log message, and so this message is actually being printed out from the this task. So, this is actually putting these messages with it's actually putting this message, content of this message sent to the queues, this message, and then this task is basically taking out oh, this is put. I'm looking at from, okay, yeah. So this guy is taking out the item from the message queue, and then it will just display it by displaying a log message of its own. So this is from this task, and this is a message that was, logged into an item of the queue. Okay, all right. So hopefully that is straightforward. Okay, atomic variables. Atomic variable is that, without the atomic variable, you could have a problem. Suppose if you want to add, increment a particular variable, there could be a chance that the multiple threads are actually interrupting each other. But using atomic variable, you can, suppose if you have atomic integer like this, and you can call a method of add and get. So basically you can add this amount of value to this integer and then get the result. And this is atomic. There is no way that somebody will interrupt this particular add and get operation. Okay, so that's atomic variable. So atomic variable code is again pretty straightforward. Main. So here we created a counter using atomic integer. Okay. So if you take a look at this code, we are basically using atomic integer. Okay, and this one has increment count method. Now we are using increment and get method. So if you take a look at the Java dog of atomic integer, you can see it does provide a multiple method: increment and get, decrement and get, add and get, and things like that. Okay, so and my runnable task is basically the calling that the increment count method, and as we have seen, increment count method using atomic integer object to increment and get. Okay, so if you run this code, you can see the values of the atomic integer is, there is no duplication. If you're not using atomic integer and multiple integer or multiple threads are actually updating a, let's say, int variable, then you could actually see, some discontinuity of this number, because another thread might in fact actually override whatever that is being worked on by another thread. Okay, the last one is logs. So log interface provides more extensive locking operation than synchronized block, and it doesn't do automatic unlocking, so you have to use a try finally to unlock it. So inside the finally, block, you have to unlock it, and you can also use the try lock. This is non-blocking. Okay, Reentrant log is concrete implementation of this log interface. So it's reentrant, meaning you can call log multiple times. So it's useful for recursive code. Read, write, and log is provided for an operation in which read and write operations are being performed. So these are the semantical behavior that you expect. So multiple threads can acquire the read log if no threads have a write log. If a thread has a read log, others can acquire read log, but nobody can acquire write log. If a thread has a write log, then nobody can have read and write log. Right? So, yeah, I mean, this kind of makes sense, right? The way that you can acquire, access these logs is you can get the read log, and from the log object you can call log method, and this one is going to return write log, and you can call the log method. Okay, so this is pretty simple code. So here we created read log and write log. Okay. First of all, you have to create the the reentrant read and write log object, which is the type of read and write log. Okay. And then you can, for whenever a user is calling get, it will log it first. Whenever user is trying to write something, it will use the write log. Whenever it's trying to clear, again, it's using write log. And all these logs need to be unlocked in the in the finally block. Okay, so let's run this code. Log. So this is a main method. So we created the basket with the logs. Well, this is our code. Okay. So if you take a look at this code, here we created reentrant write log, and then we got the read log, write log, and whenever you're trying to write something, we are going to use the write log, and then we unlock it once you write something. So here we are basically, it's a basket, shopping basket, and we are just adding the key value pair, and this is the this is read log, this is key, yeah. So this is getting the values of the key, and this is getting all the keys. So this is actually the read log, okay? And this is actually putting things, so we have to use a write log. Okay. All right. So let's run this application. So basically, it's just adding orange, and this is a key, and this is the value. So we are just adding things, okay, adding and subtracting or whatever. Okay, so that is the end of the presentation. And if you take a look at the hands-on lab documentation, basically we are using the exactly the same exercises that I have actually demonstrated as part of the presentation. So there are a couple of other exercises in this hands-on lab, but pretty much we cover all these exercises as part of the presentation. So I think we should be all set. So let me